In the early 1970s, computerized circuit analysis came into widespread use. Now, with VLSI technology, computer-aided circuit design is a necessity, not a luxury. RCAP, which stands for the Rensselaer Circuit Analysis Package, provides an interactive pre- and post-processor for SPICE, an industry-standard analysis package. When the program is first run, the user is given a blank work area on which to work. On the right side of the screen are menu options which control the functionality of the program. I've selected Parts, which brings up a Parts menu. The first Parts menu contains strictly semiconductors. As an example, I'll select a bipolar semiconductor, bipolar transistor, and place it on the screen. And I could select others. The second Parts menu contains power supplies and passive devices. As a demonstration, let me recall a circuit which is only half drawn. And complete the drawing. This will be a common emitter amplifier when we're finished. Let's first put in an AC coupling capacitor for the input, and maybe some bias resistors. Now let's wire them up. Okay. First, let's select maybe a power supply bus. And notice I did not have to route the wire. RCAP assisted in the routing. Now let's wire up the input. Notice that the node numbers are automatically changed as I wire things. For instance, wiring node 7 to node 5 results in both nodes being changed to an identical number. Okay, now let me quickly finish the drawing. Now we have a completed schematic, and the only thing left to do before actually looking at an analysis is to assign values to the components I've just added. I select the value option, and now I can choose a device on which I want to input a new value. Okay, I've selected one of the bias resistors, and I can select with the cursor the value option and input maybe a 10K resistor. And the other resistor, well, we'll make it a 1K resistor. It's an appropriate bias. And for the input capacitor, we'll make it 1 microfarad. For a closer look, let's see what the power supply parameters are. Okay, as we zoom in on, for instance, the DC value, we notice that there already is a DC offset of 0.25 volts. Well, let me change that to 0 volts. I select the option, and on the left side, the prompt says enter DC offset. I enter a 0, and the 0 value is recorded in the parameter section. We change also the AC value to, say, 50 millivolts. And maybe put a 0 time delay in and remove any phase shift we had. Okay, so now we've completely defined this power supply. I could probe around the other components. When I recalled the circuit, it had pre-assigned values already on it. So all the other values are already installed. Now we're ready to do an analysis. So I select the O-scope option, and since this is a new circuit, I have to generate a SPICE input deck. So I've selected Create Deck, and in the upper left-hand corner, the prompt says Enter Name of Circuit. And let's call this circuit Videotape. And since I already have one of those, it says, and I write over it, and I answer affirmatively. And let's put a comment card in. We'll call this a common emitter. Oops. A common emitter amplifier circuit. And there's the SPICE input deck. And the prompt now says enter maximum time I wish to look at, and I'll say 4 milliseconds. And now we're ready to look at the analysis. So I tell it to analyze videotape, and now SPICE is being run on this circuit. This tape is being made in real time, so it should take about 20 seconds before we'll see the actual analysis. The environment we're running this in is a host computer of a Prime 750, and the terminal is an Imlac 6220 vector refresh terminal. Okay, the analysis is now complete. And the circuit is redrawn in a new work area, which is much smaller than the previous one to allow room in the upper left-hand corner for a simulated oscilloscope. Let me window the circuit down a little bit so we can see the whole thing. Okay. On the oscilloscope, we can select traces by probing around the circuit. The cursor, the crosshair, is our oscilloscope probe. Let's first look at the output. Okay, the output is a sinusoid. And it's a dual trace scope, so let me also put the input up at the same time. Okay, so there's the input and the output. So it is indeed an amplifier. On the oscilloscope, I have options that you'd find on a normal oscilloscope, such as varying the time base, or changing amplifiers, or in fact, all oscilloscopic type options I have simulated here, including AC and DC coupling and putting in voltage offsets. Now that we see the results of the circuit design, we can now go back to the schematic editor and change values or change the actual circuit topography. If the circuit had gotten bigger than one work screen, RCAP allows for zooming out or zooming in fact. I could blow the circuit up. Or panning around the circuit. So in summary, what RCAP allows the user to do is design a circuit graphically without worrying about node numbers or device characteristics or conductivity or connectivity. All that is taken care of for them. And then the analysis is presented in a format that is very familiar to electrical engineers, and that is that of the oscilloscope.